Hi, Year 11. It is time to talk about the properties of ionic compounds and how they relate to their bonding. So I'm going to switch you to the PowerPoint and let's get started. You will need your booklet from the Structure and Bonding booklet, which you should have downloaded for our last video, and we will be progressing on from where we were last time. Okay, so properties of ionic compounds. This is something that you need to be able to not only know what the properties of ionic compounds are, but also to explain that in terms of their structure and bonding. So our intentions for today, we are going to learn how properties of ionic compounds are related to their structure and to their bonding, or maybe to both. And we are going to be able to work backwards, and by being given a particular set of properties, we're going to know that that compound is ionic because of its properties. So you will know you have succeeded with this if you can explain the following properties: the fact that they form crystals, the fact that they have high melting points, they're hard, brittle, don't conduct electricity when solid, but they do when they're molten or dissolved in water. And you should also be able to recognize from those properties that a substance is ionic. Let's begin. Forming of crystals. We talked about how crystals formed in our last video, and we know that the attraction of the positive and the negative ions causes them to build up a three-dimensional pattern, and that is what we call a lattice. We talked about how we were only going to talk about cubic lattice. This is really interesting. If you look at the sodium chloride lattice, then that cubic arrangement of particles, actually, if you build that up and up and up and up, you know, millions and billions of times, you end up with a crystal of salt that is actually a cube. So if you can actually form crystals of sodium chloride really slowly, so that it gives the lattice time to build up that perfect arrangement, you'll end up with a cubic crystal. So you can actually tell what the arrangement of particles in a lattice is by the shape of the crystals that they form. They have high melting temperatures. It takes a lot of energy to melt an ionic compound. In fact, ionic compounds have higher melting points normally than even metals. So why would that be? Well, if you look in the lattice structure, remember we talked about the very strong primary forces. The ionic bond was one of the strong primary forces. So that attraction between the positive and the negative ions is very strong. So in order to shake those particles so much, because if you're heating something, you're just giving it extra kinetic energy. So you're causing the particles to vibrate much faster and much harder, a little bit further off center than they would have otherwise. The more energy you give them, the more off center and the fiercer those vibrations become. And eventually we can get to a point where there is so much vibrational energy that the particle actually is removed from that lattice structure. So if you overcome the lattice energy, you can actually get that lattice to break down, and then the particles become free to move. This takes a huge amount of energy though, because you have to overcome the force of attraction of all the positives for all the negatives in the lattice to get that to melt. So it also depends on the actual strength of the charges, or the strength of the forces holding them together, which are greater if you have higher charges. So if you look at sodium chloride with the ion charges being 1 plus and 1 minus versus magnesium oxide, which is 2 plus and 2 minus, you'll see that the melting points and boiling points are hugely different, much higher for the magnesium oxide. And that just indicates that there is a much stronger force of attraction between those ions, and that is largely because of their higher charges. Hardness. You might remember back in year 8, I think, when we studied the Mohs scale of hardness for minerals, and we looked at the fact that you could determine something's hardness by how hard something had to be to scratch the surface. So for minerals, we're looking at you tried to scratch it with a copper coin, with your fingernail, with a piece of glass, and if something's harder, it will actually make a scratch on something that's softer. So hardness just refers to how difficult it is to scratch the surface of a crystal. And if you want to put a scratch on the surface of a crystal, what you're actually doing at the atomic level is ripping off a little bit of that lattice. So you're ripping off some of the ions, and that's how you would make a scratch in the lattice. And remember, the ions are held in that lattice by those very strong ionic bonds. So it's going to be very, very difficult to rip a section off and make a scratch on it. So that's why ionic compounds are hard. Even though they're hard, they are brittle. Brittle just means that when you hit them, they shatter into pieces. And when you do hit an ionic crystal hard enough, and we're talking pretty hard here, most ionic crystals, if it's a well-formed crystal, you wouldn't be able to crush it in your fingers. But if you were able to apply enough force, you could actually shatter it. And what we find is they shatter along definite flat surfaces, and they're called cleavage planes. And there's a very good reason for that. So if you look at the diagram, I've got my atomic sized hammer there. It's 1 atom in size. And we're going to smash down on that section of the lattice. So it's a very small hammer, but it's going to be able to put on a very big external force there. If you displace part of the lattice, even by 1 atom, what you can see in the middle diagram is that having just displaced that by 1 atom causes like charges to be together. So you can see the plus is next to the plus and the minus is next to the minus, and that will happen all the way through the entire lattice. And the like charges will then repel, and that's actually going to flick the 2 parts of the lattice apart. But it's going to happen all the way through the lattice, right down that line of positive next to positive and negative next to negative. And so you're actually going to get the crystal cracking down a flat plane. And that is what we call brittleness. So brittleness is just the fact that if you hit it, it tends to shatter into pieces. And you can see that that's because of the repulsion of like charges if you manage to displace that lattice. It's still not easy to displace that lattice. You've got to put a fair bit of force in. But if you smash a crystal with a hammer, then you can probably get that to occur. You probably need something a little bit larger than a 1 atom wide hammer though. Conducting electricity. Now, conducting electricity is not something that is very well understood, I find. So we're going to flick to the whiteboard and talk a little bit more about that in a minute. And metals and graphite are the only substances that can conduct electricity by a flow of electrons. And that's because those substances have electrons which are what we call delocalized. And we're going to talk a lot more about that when we talk about metallic bonding. Delocalized means they're not actually held to any particular atom. They're just kind of wandering free. So if you actually attach a battery up there, the battery's got a positive terminal, and that is going to attract the negative electrons toward it. And because they're delocalized, they're able to move around. All right, I'm going to cut. When we're talking about conduct electricity, I think it probably needs a little bit more information than that. So I'm just going to change to the whiteboard now. Fingers crossed that what we're now looking at is my picture on the whiteboard. So a battery has chemical reactions that produce and use up electrons. And we're going to do lots more of this in year 12. So we've got chemical reactions here. They produce electrons or use electrons. And what's going to happen is when the electrons are produced, we actually get the electrons coming out of the negative terminal of the battery and flowing along the wire. The reaction that uses electrons is going to cause electrons to get sucked into the positive terminal of the battery. And if we connect this circuit with a wire, what we're actually going to have is, as an electron gets produced and hops out into the wire, it's going to knock an electron along. And so if we see up here, the electron comes in here and it boots the electron onto the next atom. And then that will boot the next electron onto the next atom, and then that will kick the next electron along all the way through that wire. And that's how electricity is conducted through a metal or graphite. So it's only metals and graphite. And we're going to talk about both of those and how they conduct electricity. But the interesting thing is that electricity doesn't have to be a flow of electrons. Electricity is simply a flow of charged particles. And those charged particles for metals and graphite are electrons. So metals and graphite it's electrons. But solutions can conduct electricity as well. In solutions, the charged particles are ions. And what we see in our diagram here, is that when we take our battery and we connect it to these six, that's called an electrode. We've got another electrode over here. I feel like I'm in my Year 12 class. This is what we're learning about. And when you connect those electrodes to the battery, then you cause this one to have a negative charge because it's connected to the negative end of the battery, and you cause the other electrode to have a positive charge because it's connected to the positive charge, the positive end of the battery. And when you do that, what actually happens is that the positive ions, the cations, are going to move toward the negative electrode. On the other hand, we have the negative ions that are all going to be moving toward the positive electrode. And that is causing our flow of charged particles. So electricity can be conducted by that flow of ions as well as by a flow of electrons. And when we're talking about ionic compounds, we are talking about conducting electricity by flowing ions. Now, of course, that can't happen in a solid, because in a solid, those ions are held in place in the lattice and they can't move around because, remember, they're attracted equally in all directions by the opposite charged ions. But if we melt an ionic compound, then we've got the ions now free to move, and therefore you can have molten ionic compounds conducting electricity. The other way that you can have ions conducting electricity is by dissolving an ionic compound in water. Now, water is what we call a polar molecule. And that means that it's got a positive and a negative end. Now, this is not like having an ionic charge. This little delta minus here, that means very small negative charge. And the oxygen in the water has a very small negative charge because the electrons get pulled toward the oxygen. Much more about this next semester. The other end, the hydrogen end of the water molecule, has a slight positive charge. So it's a small positive charge. And that's because the electrons are being pulled away from it. And so it still has its protons, but its electrons are moving away from it, and that's giving it a very, very tiny positive charge. Now, the effect of those charges, if you put some salt in water, is that the negative ends of the water molecule are going to be attracted to the positive ions in the lattice. And of course, you've got millions and millions of water molecules if you're dissolving something in water. And what happens is that the water molecules come in and they surround the sodium ion and pull it out of the lattice. At the same time, for the negative ions, you've got the hydrogen ends of the water molecules being attracted into the negative ions. And again, millions and millions of them, and they come in and rip the negative ion off of the lattice. And I don't know if you've ever really closely watched something dissolve, but as crystals dissolve in water, what you first see is that they get smaller. And what you're seeing is the very outside layers of the ions being dissolved away, so that the actual crystal that's left is getting smaller and smaller because all of the ions are getting peeled off of the outside layers by the water molecules. And eventually, when we say that the substance is dissolved, is when the particles of crystal are no longer big enough for us to see. But I've got this diagram over here. Might just pull that up in size a little bit, which shows you what's actually happening. So in this first picture here, okay, it's not going to let me do that. Maybe it will. In this one here, we see that we've got the salt and all of the millions of water molecules here coming in, and they're going to be pulling the ions from the outside. And we're going to see in the second one that a lot of the ions are now surrounded by water molecules. This is called a hydration shell. So here's the sodium's hydration shell. And then if we look over here, we've also got hydration shells around the chloride ions. And that allows, once the ions have been pulled off into their hydration shells, they can actually move around. And when the substance is totally dissolved, like in the third diagram there, we have those ions all in hydration shells, and there's all water molecules. There's more waters in the middle here. Not all the waters are involved in hydration shells. And that actually, we have the ions just bobbing around in the water. All right, I'm going back to the PowerPoint now, I hope. Here we go. So when we're talking about conducting electricity, it doesn't have to be moving electrons. It can be any charged particles, so electrons and ions. So if you've got a molten salt, if you take some sodium chloride and heat it up between about 800 degrees and 1400 degrees, it will melt. And then the ions have been freed from those lattice positions and can move around. And that flow of ions is going to create electricity. Of course, we have the same thing when we have the ionic compound dissolved in water. And if you want to have an electric current flowing, there are two conditions that need to be met. Firstly, you have to have some charged particles. And secondly, the charged particles must be free to move. So it is not good enough to only have one of those. You can't have charged particles that can't move. You won't get electric current. And if you don't have charged particles, you can't get an electric current flowing. So if we look at our examples, diagram A, pure water. Pure water doesn't have charged particles. Even though the water molecules are polar, that's not a full charge. So pure water doesn't conduct electricity. Now, second, in the middle example, solid sodium chloride doesn't conduct electricity. It does have charged particles, but they're locked in place, so they can't move. You've got to satisfy both conditions to get the electricity conducted. And then the final one, in sodium chloride dissolved in water, we do get an electric current because we have both charged particles and they are free to move. So we look at conducting in ionic compounds. In the solid, if we look in the table, the solid, yes, it has charged particles, but no, they can't move. So overall, that's a no on current flow. But for molten and solution, we have charged particles, they can move, and therefore we can get an electric current to flow. Okay, that's it for today. I will see you in the next video.